Close your eyes for a moment and picture the night sky. Not the sky from your backyard, washed out by streetlights and city glow, but the sky from somewhere truly remote. Perhaps you're standing in a desert, miles from any town, or on a mountain peak where the air is thin and crystal clear. When you open your eyes in this imagined place, what do you see? Thousands of pinpricks of light scattered across an endless canvas of perfect darkness. Stars, planets, the misty band of the Milky Way stretching overhead like a river of light frozen in time. Now consider this. Those points of light you're seeing represent an almost incomprehensibly small fraction of what's actually out there. Our universe contains somewhere between 200 billion trillion and a septillion stars. That's a number so vast that if you tried to count them, giving each star just 1 second of your time, you'd be counting for trillions of years longer than the universe has existed. Each of those stars is a massive nuclear furnace, many of them far more luminous than our own sun, pouring unimaginable amounts of light into the cosmos every single second. And yet, when you look up at that night sky, when astronauts float in the void between worlds, when our spacecraft journey to the outer reaches of the solar system and point their cameras away from the sun, they all encounter the same profound reality. Space is black. Deeply, utterly, overwhelmingly black. The darkness between the stars isn't just an absence of light in a few scattered places. It's everywhere. It dominates. It defines the cosmos. This is one of the most beautiful contradictions in all of nature. How can space be so dark when it's absolutely flooded with light? How can a universe containing more stars than there are grains of sand on all of Earth's beaches appear to us as an ocean of darkness punctuated by tiny islands of light, rather than a brilliant, all-encompassing glow? This question has puzzled humanity for centuries, and the answer reveals some of the most profound truths about the nature of our universe. The darkness of space is so absolute that it challenges our everyday understanding of light and shadow. When you stand in a room with a single candle, the light from that flame bounces off the walls, the ceiling, the furniture, creating a gentle ambient glow that allows you to see even the corners not directly illuminated. The light scatters, reflects, fills the space. But in the cosmos, this doesn't happen. A star can be blazing with the light of 1 billion suns, and yet the space immediately surrounding it remains pitch black. There's no ambient glow, no diffuse illumination, just points of brilliance floating in absolute darkness. This phenomenon becomes even more striking when we consider the sheer quantity of light in the universe. Every second, our sun alone radiates approximately 3.8 times 10 to the 26th watts of power into space. To put that in perspective, that's more energy than all of human civilization has used throughout its entire history, released every single second. And our sun is just one relatively average star among hundreds of billions in our galaxy alone. Multiply that by the trillions of galaxies in the observable universe, and you begin to grasp the staggering amount of light energy permeating space. The ancient night sky watchers noticed something curious. They could see perhaps 6,000 stars with the naked eye on the clearest nights scattered across the celestial sphere. But between these stars lay darkness. This seemed natural enough to them, but as human understanding of the cosmos grew, this observation became increasingly puzzling. If the universe was infinite and filled with stars in every direction, shouldn't every line of sight eventually end on the surface of a star? Shouldn't the entire sky be as bright as the sun? This puzzle would eventually be formalized into what we now call Olbers's paradox, named after the German astronomer Heinrich Wilhelm Olbers, though the question had been posed by thinkers going back to Johannes Kepler in the early 1600s. It's a paradox because it reveals a fundamental contradiction between a simple, logical assumption about the universe and what we actually observe. If space goes on forever and contains stars throughout, then the night sky should be uniformly bright. But it's not. It's dark. Profoundly, beautifully dark. Understanding why space is black despite being full of light requires us to embark on a journey through some of the most fascinating concepts in modern astrophysics. We'll need to understand the nature of light itself, the structure and history of the universe, the way space itself behaves, and even the limitations imposed by the cosmic speed limit. We'll discover that the darkness of space isn't a simple thing with a simple explanation. Instead, it's the result of multiple factors working together, each one contributing to the cosmic darkness we observe. The answer to this question isn't just academic curiosity. The darkness of space is actually one of the strongest pieces of evidence we have for the Big Bang Theory and the expansion of the universe. It tells us that our cosmos had a beginning, that it's been growing and changing over time, and that it has a specific structure and history. In a very real sense, the darkness between the stars is a window into the fundamental nature of reality itself. As we explore this question together, we'll travel from the subatomic scale where light is born to the largest structures in the cosmos. We'll watch the universe expand, witness the birth and death of stars, and peer into the deepest voids that exist. We'll discover that space isn't really empty at all, but filled with invisible forms of light, ancient radiation from the birth of the universe, and mysterious dark energy that's pushing everything apart. And through it all, we'll come to appreciate that the darkness of space, far from being an absence or a void, is actually a profound presence that shapes and defines our cosmic home. So, settle in for this journey into darkness and light. Let's unravel one of the universe's most captivating mysteries together. Before we can truly understand why space is black, we need to grasp what light actually is and how it behaves. Light is one of those phenomena that seems simple on the surface, but reveals incredible complexity the deeper you look. At its most fundamental level, light is a form of electromagnetic radiation, a disturbance in the electromagnetic field that permeates all of space. It's simultaneously a wave and a particle, displaying properties of both depending on how we observe it. When we think about light as a wave, we're envisioning something like ripples spreading across a pond, except these ripples are oscillations in electric and magnetic fields rather than in water. These waves have specific properties: wavelength, which is the distance from one wave crest to the next, and frequency, which is how many wave crests pass a given point each second. The relationship between these properties determines the energy of the light and where it falls on the electromagnetic spectrum. The electromagnetic spectrum is vast, stretching from radio waves with wavelengths of kilometers down to gamma rays with wavelengths smaller than an atom. Visible light, the light our eyes can detect, occupies just a tiny sliver of this spectrum. The longest wavelengths we can see appear red to us at around 700 nanometers. The shortest visible wavelengths appear violet at around 390 nanometers. Between these extremes lie all the colors of the rainbow: red blending to orange, to yellow, to green, to blue, to indigo, to violet. But light can also behave as a particle. These particles of light are called photons, and they're massless packages of energy that travel through space at the ultimate cosmic speed limit, approximately 299,792,458 meters per second in a vacuum. This speed is so fundamental to the universe that we call it c in physics equations. And it's not just the speed of light, but the speed at which all massless particles must travel and the speed at which causality itself propagates through space. When a photon is created, perhaps by an electron dropping to a lower energy level in an atom, or by nuclear fusion in the core of a star, or by charged particles accelerating, it begins its journey through space. In a vacuum, that journey is remarkably simple. The photon travels in a perfectly straight line at the speed of light, never slowing down, never speeding up, never deviating from its path unless it encounters matter or is affected by gravity. This is crucial to understanding the darkness of space. Light in a vacuum travels in straight lines and doesn't spread out or scatter the way it does in a material medium. This brings us to the question of darkness. What is darkness really? In our everyday experience, darkness is the absence of light. We flip a switch, the lights go out, and the room becomes dark. But this everyday darkness is rarely absolute. Even in a darkened room, there's usually some light creeping in from under doors, through windows, from glowing electronic devices. Our eyes adapt, and we can often make out shapes and shadows. This is because light in our atmosphere scatters and bounces around, finding paths into even the darkest corners. True darkness, absolute darkness, is something different. It's the complete absence of photons, no light of any wavelength. This kind of darkness is rare on Earth, difficult to achieve even in carefully designed laboratory conditions. But in space, far from any stars or galaxies, absolute darkness becomes the norm rather than the exception. This is because space is, to an excellent approximation, a vacuum. The vacuum of space is the closest thing nature provides to true nothingness. In the interstellar medium, the space between stars within a galaxy, there's typically 1 atom per cubic centimeter. In the intergalactic medium, the space between galaxies, the density drops even further, to perhaps 1 atom per cubic meter. In the deepest cosmic voids, it can be 100 times less than that. Compare this to Earth's atmosphere at sea level, which contains about 2.5 times 10 to the 19th molecules per cubic centimeter. Space is extraordinarily empty. This emptiness is crucial to understanding the darkness of space. When light travels through a material medium like air or water, it constantly interacts with the atoms and molecules it encounters. These interactions cause the light to scatter, to change direction, to bounce around. Some wavelengths scatter more than others, which is why Earth's sky is blue and sunsets are red. But in the vacuum of space, there are so few particles that this scattering essentially doesn't happen. A photon can travel for billions of light years through intergalactic space without encountering a single atom. Think about what this means for a moment. When you're in a room lit by a lamp, you can see not just the lamp itself, but also the walls, the floor, the objects around you. This is because photons from the lamp are scattering off these surfaces and into your eyes. The room is filled with light bouncing in every direction. But in space, this doesn't occur. A photon travels from its source in one direction at the speed of light in a perfectly straight line. Unless that photon happens to travel directly into your eye, or your telescope, or your camera, you'll never detect it. It's as if the photon doesn't exist for you. This is why astronauts in space, even in direct sunlight, see a black sky. The sun illuminates one side of the Earth brilliantly, but when they look away from the sun and Earth, they see only the blackness of space dotted with stars. The photons streaming from the sun aren't scattering in the vacuum around them. There's nothing for them to scatter off of, so unless they're looking directly at something that's emitting or reflecting light, they see darkness. The behavior of light in a vacuum is described by Maxwell's equations, a set of 4 elegant mathematical relationships that govern all electromagnetic phenomena. These equations tell us that, in a vacuum, electromagnetic waves propagate without loss of energy, traveling indefinitely until they encounter matter. They don't slow down, don't disperse, don't fade away through scattering. This is why we can see light from galaxies billions of light years away. The photons that left those galaxies billions of years ago have traveled across the cosmos, through the vast emptiness of intergalactic space, to reach our telescopes today. But not all light travels through space entirely unimpeded. Gravity can bend the path of light, an effect predicted by Einstein's general theory of relativity and confirmed through numerous observations. Strong gravitational fields, like those around massive galaxy clusters or black holes, can noticeably curve the trajectory of passing photons. This gravitational lensing can magnify distant objects, allowing us to see things that would otherwise be too far away or too faint to detect. But even when light is bent by gravity, it doesn't scatter or diffuse. It still travels in straight lines through the curved spacetime itself. The quantum nature of light adds another layer of understanding. Photons are quantum objects, meaning they can exist in superpositions of states and display wave-particle duality. When a photon is traveling through space, it exists as a probability wave, spread out over some region of space. But when it's detected, when it interacts with an atom in your eye's retina, for example, this probability wave collapses, and the photon is localized to a specific point. This quantum behavior doesn't change the fact that photons travel in straight lines in a vacuum, but it does influence phenomena like interference and diffraction at very small scales. Understanding these properties of light helps us appreciate why space appears dark. Light doesn't illuminate space itself. It only illuminates objects it hits. The blackness between stars isn't a failure of the stars to produce enough light. It's simply a consequence of the fact that in the vacuum of space, light travels from source to destination without scattering, without filling the space between them with a visible glow. The light is there, streaming past in uncountable numbers of photons every second, but unless those photons enter your eye directly, you don't see them. This is fundamentally different from our experience on Earth, where the atmosphere creates a diffuse glow. During the day, even when you're not looking directly at the sun, the sky is bright blue because sunlight is scattering off nitrogen and oxygen, molecules in all directions. At night, even though the sun is gone, light from the moon, stars, and human sources scatters through the atmosphere, creating air glow and sky glow that prevent the sky from being truly black. In space, none of this happens. Each star is a point of light in an ocean of darkness, and all the light streaming from it travels directly outward without illuminating the space between. To truly appreciate why space is black, it helps to understand why Earth's sky isn't. Every day, billions of people look up during daylight hours and see a beautiful blue sky. This blue isn't a property of space itself or of the sun's light. It's a consequence of our atmosphere and the way it interacts with sunlight. This interaction, called Rayleigh scattering, is the key to understanding one of the major differences between Earth and space. The sun emits light across a broad spectrum of wavelengths, from ultraviolet through visible light to infrared. When this white light from the sun enters Earth's atmosphere, it encounters trillions upon trillions of gas molecules, primarily nitrogen and oxygen. These molecules are tiny compared to the wavelength of visible light, and when light waves interact with such small particles, something interesting happens. The light scatters. Scattering means that the light changes direction without losing energy. A photon traveling from the sun might be heading straight down toward Earth's surface, but when it encounters an air molecule, it can bounce off in a completely different direction. This isn't reflection in the mirror sense. The molecule isn't like a tiny mirror sending the light back where it came from. Instead, the interaction between the light wave and the molecule's electrons causes the light to radiate in all directions, with some directions being more probable than others. Lord Rayleigh, a British physicist working in the 1870s, figured out the mathematics of this scattering. He discovered that the amount of scattering depends strongly on the wavelength of the light. Specifically, the intensity of scattered light is inversely proportional to the fourth power of the wavelength. This relationship, I over lambda to the fourth, means that shorter wavelengths scatter much more strongly than longer wavelengths. Let's put some numbers to this. Blue light has a wavelength of about 470 nanometers, while red light has a wavelength of about 650 nanometers. When we calculate the scattering ratio using Rayleigh's formula, we find that blue light scatters approximately 9 times more strongly than red light. This means that for every red photon that gets scattered by the atmosphere, 9 blue photons get scattered in the same volume of air. This is why our sky is blue. When sunlight enters the atmosphere, the blue and violet wavelengths scatter far more than the longer wavelengths. This scattered blue light comes at us from all directions of the sky, creating the azure dome we see overhead. The longer wavelengths, the reds and oranges and yellows, mostly pass straight through the atmosphere without scattering as much, which is why the sun itself appears yellowish-white when viewed from Earth's surface. You might wonder why the sky isn't violet, since violet light has even shorter wavelengths than blue and should scatter even more strongly. The reason is twofold. First, the sun actually produces less violet light than blue light to begin with. Second, our eyes are more sensitive to blue wavelengths than violet wavelengths, so even though some violet light is scattered, we perceive the sky as blue rather than violet. At sunset and sunrise, we see a different phenomenon. When the sun is near the horizon, its light must travel through a much greater thickness of atmosphere to reach our eyes. This longer path means that even more of the blue light gets scattered away before the light reaches us. What remains are the longer wavelengths that can penetrate through more air, the oranges, reds, and deep crimsons that paint the sky during these golden hours. The scattered blue light isn't gone, it's illuminating other parts of the sky and creating daylight for people elsewhere. The process of Rayleigh scattering is incredibly efficient at filling Earth's atmosphere with diffuse light. Even when you're standing in the shadow of a building during the day, it's not dark. Light has scattered into that shadow from all over the sky. The entire atmosphere becomes, in effect, a giant diffuser, taking the directed beam of sunlight and turning it into an omnidirectional glow. This is why photographers and filmmakers love diffused light. It's soft, even, and flattering. But it's also why we can't see stars during the day. The scattered sunlight in the atmosphere is so much brighter than the light from distant stars that it overwhelms them. Now consider what happens in space. There is no atmosphere, or effectively none. The density of particles in space is so low that scattering becomes negligible. A photon from the sun, or from any star, travels in a straight line until it hits something solid. This is why when astronauts look up from the moon's surface, they see a black sky even during the lunar day. The sun is a brilliant point of light. The lunar surface around them is brightly illuminated, but the sky above is the same black expanse dotted with stars that they would see during the lunar night. Astronaut descriptions of space from orbit or from the moon consistently emphasize this profound darkness. Eugene Cernan, the last person to walk on the moon during Apollo 17, described looking up into the blackest black he had ever seen. The contrast between the brightly sunlit lunar surface and the black sky above was so stark it was almost disorienting. He could see more stars than he'd ever seen from Earth, appearing with perfect clarity because there was no atmosphere to scatter their light, or to create a competing glow. This absence of scattering in space means that shadows are absolute. On Earth, even in direct sunlight, shadows are partially filled in by scattered light from the atmosphere. You can see detail in shadowed areas because blue skylight illuminates them. But in space, shadows are pure black. No light scatters into them. This creates the high contrast conditions visible in photographs from the moon, where sunlit areas are brilliantly bright and shadowed areas are completely dark, with no gradual transition between them. The physics of atmospheric scattering also explains other phenomena we see on Earth. The white appearance of clouds is due to me-scattering, which occurs when light interacts with particles that are comparable in size to the wavelength of light, such as water droplets. Unlike Rayleigh scattering, me-scattering affects all wavelengths roughly equally, which is why clouds appear white. They're scattering all colors of sunlight equally. The haziness we sometimes see in polluted or dusty air is also due to me-scattering from larger particles. The amount of atmosphere above you also affects the color and brightness of the sky. At higher altitudes, where the air is thinner, the sky takes on a deeper blue color because there are fewer molecules to scatter the light. Mountain climbers at high altitude report that the sky appears darker blue, almost purple in extreme cases. Astronauts in near-Earth orbit, above most of the atmosphere, see an even darker sky. As you go higher, the transition from the blue sky we know to the black sky of space is gradual, with the atmosphere's glow fading away as the density of scattering particles decreases. Understanding Rayleigh scattering and the role of Earth's atmosphere helps us appreciate that the darkness of space is, in part, simply the natural state of a vacuum. Without an atmosphere to scatter light in all directions, to create diffuse illumination, to fill in the spaces between light sources, we see space as it truly is, individual points and patches of light separated by vast stretches of darkness. The light is traveling everywhere in countless directions, but we only see the photons that happen to be traveling toward our eyes from their sources. This also helps explain why space-based telescopes like the Hubble Space Telescope and the James Webb Space Telescope can see such faint and distant objects. They're operating above the atmosphere, where there's no scattered light to compete with the faint signals from distant galaxies. The background is perfectly black, allowing even extremely faint sources to stand out. This is one reason why space telescopes despite sometimes having smaller mirrors than ground-based telescopes, can achieve such remarkable results. The lesson here is fundamental. Space isn't black because it lacks light. Space is black because it lacks the medium necessary to scatter that light, to make it visible from all angles, to create the kind of diffuse illumination we experience on Earth. The darkness of space is a property of the vacuum, not a property of the light itself. The question of why the night sky is dark despite being filled with stars has puzzled thinkers for centuries, and it crystallized into what we now call Olbers' paradox. This apparent contradiction between observation and expectation became one of the great mysteries of astronomy, and solving it required nothing less than understanding the true nature and history of our universe. The paradox is deceptively simple to state. If we assume that the universe is infinite in size, eternal in age, and uniformly filled with stars, then every line of sight from Earth should eventually intersect the surface of a star. Imagine standing in an infinitely large forest, where trees are distributed evenly throughout. No matter which direction you look, your line of sight will eventually hit a tree trunk. Apply this same logic to stars in an infinite universe, and you arrive at a startling conclusion. The entire night sky should be as bright as the surface of the sun. Let's work through the logic more carefully. Consider dividing the universe into a series of concentric shells around Earth, each shell representing stars at a particular distance. The first shell might contain stars between 100 and 101 light-years away. The second shell contains stars between 200 and 201 light-years away. The third shell between 300 and 301 light-years away, and so on, extending outward infinitely. Now, each star has a certain luminosity. It gives off a certain amount of light. But as that light travels outward, it spreads out over an increasingly large area. This is the inverse square law of light. If you double your distance from a star, its brightness decreases by a factor of 4. If you triple the distance, brightness decreases by a factor of 9. At distance d from a star, the light is spread over a sphere of area 4 πd squared, so the brightness we observe decreases as 1 over d squared. But here's where it gets interesting. As we go to more distant shells, even though each individual star appears fainter, there are more stars in the shell. The volume of a shell increases with the square of its distance. A shell at twice the distance has 4 times the volume and thus 4 times as many stars, assuming uniform density. These two effects, stars getting fainter with distance squared and the number of stars increasing with distance squared, exactly cancel out. This means that each shell of stars, no matter how distant, contributes the same total amount of light to Earth's sky. The nearby shell has bright stars, but few of them. The distant shell has faint stars, but many of them. The total contribution is identical, and if there are infinite shells extending outward forever, the total brightness should be infinite, or at least enormous enough to make the entire sky as bright as the surface of a typical star. This conclusion is clearly at odds with reality. When we look at the night sky, we see individual stars separated by darkness. The integrated brightness of all the stars visible to the naked eye is nowhere near enough to rival the sun. Even with powerful telescopes that reveal billions more stars, vast regions of the sky between them remain dark. The paradox demands an explanation. Heinrich Wilhelm Olbers published a paper in 1826 discussing this problem, though he was far from the first to consider it. Johannes Kepler had raised similar questions in 1610, arguing that if the universe were infinite, we wouldn't see the darkness we observe. He concluded that the universe must be finite, with the stars ending at some distance. Edmond Halley and Jean-Philippe Loy de Chezeaux in the 18th century had also grappled with the question. Over the years, various solutions were proposed to resolve the paradox. One early suggestion was that interstellar dust absorbs the light from distant stars, preventing it from reaching us. This seems plausible at first. We know dust exists in space and does block light. However, this solution fails when you consider thermodynamics. If dust were absorbing all that starlight, it would heat up. Eventually, it would reach the same temperature as the stars themselves and would start glowing just as brightly, recreating the original problem. Another proposed solution involved the possibility that stars are not uniformly distributed. Perhaps they cluster in certain regions, leaving vast empty spaces between clusters. While this is actually true to some extent, stars do cluster in galaxies, and galaxies cluster in groups and superclusters, it doesn't resolve the fundamental issue. In an infinite universe, even if matter is clumpy on small scales, on large enough scales you'd expect the distribution to average out to something roughly uniform. And even if it didn't, you'd eventually see more distant clusters filling in the gaps. Some thinkers suggested that the inverse square law might break down over cosmic distances, that light might somehow fade or get tired as it travels across the universe. This tired light hypothesis had some appeal, but it contradicts what we know about the behavior of electromagnetic radiation in a vacuum. Photons don't lose energy simply by traveling through empty space. They maintain their energy indefinitely unless they interact with something. The true solution to Olbers's paradox requires us to abandon one or more of the fundamental assumptions built into the problem. The paradox assumes the universe is infinite in size, eternal in age, static, not expanding or contracting, and uniformly filled with stars that have always been shining. As it turns out, every one of these assumptions is wrong. The universe is not eternal. It had a beginning approximately 13.8 billion years ago in idle, the event we call the Big Bang. This immediately solves a major part of the paradox. Because the universe has a finite age, we can only see light from stars and galaxies whose light has had time to reach us. Light travels at a finite speed, the speed of light, so there's a horizon beyond which we cannot see. No matter how many stars might exist beyond that horizon, their light hasn't had time to reach us yet, so they don't contribute to the brightness of our sky. Think of it this way. A star located 15 billion light-years away is out there, perhaps shining brightly. But its light, traveling toward Earth at the speed of light, has only been traveling for 15 billion years. Since the universe is only 13.8 billion years old, and that star didn't exist at the very beginning, its light hasn't reached us yet. We can't see it. It doesn't make our sky brighter. There's a cosmic horizon of visibility determined by the age of the universe and the speed of light. But the finite age of the universe is only part of the solution. The universe is also expanding, and this expansion plays a crucial role in explaining the darkness of the night sky. As space itself expands, it stretches the wavelength of light traveling through it. This cosmological redshift shifts light toward longer wavelengths and lower energies. Light that was emitted as ultraviolet or visible light from very distant galaxies gets stretched so much by the expansion of space that by the time it reaches us, it's shifted into the infrared, or even microwave wavelengths, wavelengths our eyes can't detect. Furthermore, the expansion means that very distant galaxies are receding from us at speeds that approach or even exceed the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Rather, the space between us and them is expanding. But the practical effect is the same. Light from the most distant parts of the universe is redshifted so dramatically that it contributes essentially nothing to the visible brightness of our sky. The universe is also not static and unchanging. Stars have finite lifetimes. They form, burn for a period ranging from millions to trillions of years depending on their mass, and then die. Even if the universe were eternal, not all regions of space have been continually filled with shining stars. There are periods in cosmic history when, and places in cosmic space, where stars haven't formed yet or have already burned out. The density and distribution of stars changes over time. Solving Olbers's paradox required some of the most profound insights in the history of science. It required understanding that the universe had a beginning, that it's expanding, that light has a finite speed, and that cosmic structure evolves over time. The darkness of the night sky isn't just a curious observation, it's direct evidence for the Big Bang and the finite age of our universe. As astrophysicist Robert Harrison has pointed out, if you want proof that the Big Bang happened, you need only venture outside at night and notice that the sky is dark. This makes the darkness of space profoundly meaningful. Every time you look up at a star-filled sky and notice the darkness between those stars, you're seeing evidence of the universe's history written in light and shadow. You're seeing the consequences of the Big Bang, of cosmic expansion, of the finite speed at which information can travel through space. The darkness isn't empty. It's full of information about how our universe came to be and how it behaves. Understanding why space is black requires grappling with one of the most fundamental facts about our universe. It had a beginning. This beginning, which we call the Big Bang, occurred approximately 13.8 billion years ago. This isn't just a large number, it's a precise measurement that has profound implications for what we can and cannot see when we look out into space. The age of the universe has been measured through multiple independent methods, all of which converge on the same approximate value. One method examines the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. By analyzing the tiny temperature variations in this radiation, cosmologists can extract detailed information about the early universe and calculate its age. The European Space Agency's Planck satellite, which operated from 2009 to 2013, produced the most precise measurements to date, determining the universe's age as 13.787 billion years, with an uncertainty of only 20 million years either way. Another method for determining cosmic age involves measuring the expansion rate of the universe, known as the Hubble constant, and using it to calculate how long the universe has been expanding. Still another approach examines the oldest known stars and stellar populations, which provide a lower limit on the universe's age. The universe must be at least as old as its oldest stars. Remarkably, all these different approaches agree, giving us confidence that we truly know how old our universe is. This finite age immediately imposes a fundamental limit on what we can observe. Light travels at a fixed speed, approximately 299,792,458 meters per second. Nothing in the universe can travel faster than this speed through space. This means that in the 13.8 billion years since the Big Bang, light has only been able to travel a certain maximum distance. Objects farther away than this distance are beyond our cosmic horizon. Their light simply hasn't had time to reach us yet. At first glance, you might think this means we can see objects up to 13.8 billion light-years away and no farther. But the reality is more complex because the universe itself is expanding. As light travels through space, space itself is stretching, carrying distant galaxies away from us. This means that a galaxy whose light has taken 13 billion years to reach us isn't 13 billion light-years away right now. It's much farther away because space has been expanding during all those billions of years that its light was traveling toward us. When we account for cosmic expansion, the most distant objects we can theoretically see are in what's called the observable universe, which has a radius of about 46.5 billion light-years. This is larger than 13.8 billion light-years because of the expansion that's occurred during the light travel time. A galaxy at the edge of the observable universe emitted its light nearly 13.8 billion years ago when the universe was very young. But during those billions of years, space has been expanding, carrying that galaxy farther and farther away. Today, that galaxy is 46.5 billion light-years distant. This observable universe is like a sphere centered on Earth, encompassing everything from which light has had time to reach us since the Big Bang. But here's the crucial point. This is almost certainly not the entire universe. The actual universe is likely much larger, perhaps infinitely larger, than the observable universe. But everything beyond our cosmic horizon is invisible to us. It doesn't matter how many stars or galaxies exist out there, their light hasn't reached us, so they contribute nothing to the brightness of our sky. This immediately resolves a major part of Olber's paradox. Even if stars extended infinitely in all directions, we can only see the ones within our observable universe. This is a finite number of stars, roughly 200 billion trillion, or 2 sextillion, rather than an infinite number. While this is an almost incomprehensibly large number, it's still finite, and those stars are spread across an enormous volume of space. The expansion of the universe adds another crucial element to understanding cosmic darkness. The expansion isn't like an explosion where matter flies outward from a central point into empty space. Rather, space itself is expanding, carrying galaxies along with it. Imagine a balloon with dots marked on its surface. As you inflate the balloon, the dots move apart from each other, not because they're moving across the balloon's surface, but because the surface itself is stretching. This is analogous to how cosmic expansion works, except in 3 dimensions rather than 2. Edwin Hubble discovered this expansion in 1929 by observing that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, now called Hubble's law, states that recession velocity equals the Hubble constant times distance. The Hubble constant describes the rate of expansion and has been measured at approximately 70 kilometers per second per megaparsec. This means that a galaxy 1 megaparsec away, about 3.26 million light-years, is receding from us at 70 kilometers per second, while a galaxy 2 megaparsecs away is receding at 140 kilometers per second. As distances increase, recession velocities increase proportionally. At great enough distances, galaxies are receding from us faster than the speed of light. This doesn't violate Einstein's relativity because the galaxies aren't moving through space faster than light. Instead, space between us and them is expanding. But the practical effect is dramatic. Light from these ultra-distant galaxies is stretched by the expansion to such an extent that it shifts out of the visible spectrum entirely. This brings us to one of the most important concepts for understanding the darkness of space: cosmological redshift. When light travels through expanding space, its wavelength gets stretched along with the expansion of space itself. Light emitted as blue might arrive as red. Light emitted as red might arrive as infrared. Light emitted as visible might arrive as microwaves. The amount of stretching depends on how much space has expanded during the light's journey, which depends on the distance the light has traveled and the rate of expansion. Cosmologists quantify this stretching using a parameter called redshift, denoted by the letter Z. A redshift of Z equals 1 means that wavelengths have been stretched by a factor of 2, doubled. A redshift of Z equals 2 means wavelengths have been tripled. The most distant galaxies we've observed have redshifts of Z equals 10 or more, meaning their light has been stretched by a factor of 11 or more. A photon that left such a galaxy as ultraviolet light arrives at Earth as infrared light. This redshift has enormous implications for the darkness of space. Many distant galaxies that would appear bright if they were nearby are so redshifted that most of their light falls outside the visible spectrum. We can detect them with infrared telescopes like the James Webb Space Telescope, but they contribute little or nothing to the visible brightness of the sky. In effect, a large fraction of the light in the universe has been rendered invisible by the expansion of space. The expansion also means that the universe was much smaller and denser in the past. If we run the expansion backward in time, we see that all the matter and energy in the universe was once compressed into an incredibly small, hot, dense state. This is the Big Bang, not an explosion in space, but an expansion of space itself, from an initial state of extreme density and temperature. In the first moments after the Big Bang, the universe was so hot and dense that it was opaque to light. Photons couldn't travel freely. They were constantly scattering off the dense plasma of charged particles. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons to combine with atomic nuclei to form neutral atoms. This event, called recombination, rendered the universe transparent. Photons could suddenly travel freely through space. The light from this epoch, stretched by billions of years of cosmic expansion, is what we now detect as the cosmic microwave background radiation, a subject we'll explore in more depth shortly. The finite age of the universe, combined with the expansion of space, creates a 1-2 punch against cosmic brightness. First, we can only see light from objects whose light has had time to reach us, a finite number of sources. Second, light from the most distant sources has been stretched by expansion to wavelengths our eyes can't detect. Together, these factors ensure that despite the vast number of stars and galaxies in existence, only a relative handful contribute significantly to the visible brightness of our sky. Recent observations have revealed that the expansion of the universe is accelerating. The most distant galaxies are receding from us faster than we would expect based on the standard expansion rate. This acceleration is attributed to dark energy, a mysterious form of energy that permeates all of space and drives the expansion to speed up over time. Dark energy makes up about 68% of the total energy content of the universe, yet we know very little about its nature. This accelerating expansion has a sobering implication for the far future. Galaxies that are already very distant will be carried away from us ever faster. Eventually, they'll recede so quickly that no light they emit from that point onward will ever reach us. The observable universe will actually shrink in terms of the number of galaxies visible to us. Billions of years from now, observers in the Milky Way will see fewer galaxies in their night sky than we see today. The darkness of space, in this sense, will deepen over cosmic time. The history of the universe is written in the light we receive from distant objects. When we look at a galaxy 1 billion light-years away, we're seeing it as it was 1 billion years ago. When we look at a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago, when the universe was only about a quarter of its current age. The most distant galaxies, visible with our best telescopes, appear as they were when the universe was only a few 100 million years old, just forming their first generation of stars. This means that the light filling space comes from different eras of cosmic history. The nearest stars show us the present. More distant galaxies show us the past. The most distant objects show us the early universe, so young that it was dramatically different from the cosmos we see nearby. The darkness between these objects represents not just empty space, but also gaps in cosmic time, eras and locations from which light hasn't yet reached us or has been shifted beyond our detection. Capabilities. The expansion of the universe, combined with its finite age, fundamentally shapes the appearance of the cosmos. These factors ensure that no matter how many light sources exist in the universe, we see only a finite subset of them, and many we do see are dimmed and redshifted by their great distance and the expansion of space. The darkness we observe isn't a failure of the universe to produce enough light. It's a direct consequence of the universe's history and evolution, a natural result of living in an expanding cosmos that had a beginning. To fully appreciate how cosmic expansion contributes to the darkness of space, we need to explore redshift in greater detail. Redshift is one of the most important concepts in modern cosmology, and understanding it reveals why so much of the universe's light is hidden from our eyes. You're probably familiar with the Doppler effect, which describes how waves change frequency when their source is moving relative to an observer. When an ambulance approaches you with its siren blaring, the sound waves get compressed, raising the pitch. As the ambulance moves away, the sound waves get stretched out, lowering the pitch. The same principle applies to light. If a light source moves toward you, its light waves get compressed, shifting toward shorter wavelengths, toward the blue end of the spectrum. This is called blue shift. If a light source moves away from you, its light waves get stretched, shifting toward longer wavelengths, toward the red end of the spectrum. This is called redshift. The Doppler effect explains some of the redshift we observe in the universe, particularly for nearby objects. But for distant galaxies, something more profound is happening. The redshift isn't primarily due to galaxies moving through space. It's due to space itself expanding and carrying the galaxies with it. This is called cosmological redshift, and it differs from the Doppler effect in important ways. When a photon is emitted from a distant galaxy, it begins its journey through space with a particular wavelength determined by the atomic transition that created it. As the photon travels, space itself expands. This expansion stretches the photon's wavelength along with everything else. By the time the photon reaches us, its wavelength has been increased by the same factor that space has expanded during its journey. If space doubled in size during the photon's trip, the wavelength doubled. If space expanded by a factor of 10, the wavelength increased by a factor of 10. Let's consider a concrete example. Hydrogen atoms, the most abundant element in the universe, emit light at very specific wavelengths when their electrons transition between energy levels. One prominent line, called the hydrogen alpha line, has a wavelength of 656.3 nanometers in the red part of the spectrum. When we observe light from a distant galaxy, we can identify this hydrogen line, but we find it shifted to a longer wavelength. Suppose we observe a galaxy where the hydrogen alpha line appears at 984.5 nanometers instead of its normal 656.3 nanometers. The ratio of observed wavelength to emitted wavelength is 984.5 divided by 656.3, which equals 1.5. This means the wavelength has been stretched by 50%, or the galaxy has a redshift of z equals 0.5. This tells us that space has expanded by a factor of 1.5, or 50%, since the light was emitted from that galaxy. We can work backward from the redshift to determine when the light was emitted and how far away the galaxy is now. A redshift of 0.5 corresponds to looking back about 5 billion years in cosmic time, when the universe was roughly 2/3 of its current age. The galaxy that emitted this light is now about 6 billion light-years away, having been carried farther by the expansion during the 5 billion years its light was traveling toward us. As we look at more and more distant galaxies, we find larger and larger redshifts. Galaxies with redshifts of z equals 1 have had their light wavelengths doubled. Galaxies with redshifts of z equals 2 have had wavelengths tripled. The most distant galaxies, observed with current technology, have redshifts of z equals 10 or more, meaning their light wavelengths have been stretched by a factor of 11 or more. This extreme stretching has dramatic effects on what we can see. Consider a galaxy emitting most of its light in the ultraviolet part of the spectrum, around 300 nanometers. If this galaxy has a redshift of z equals 9, meaning wavelengths have been stretched by a factor of 10, that ultraviolet light arrives at Earth at 3000 nanometers, well into the infrared range. None of the light that was visible when emitted remains visible when it reaches us. The entire galaxy has been redshifted out of the visible spectrum. This is happening to countless galaxies throughout the observable universe. The farther away a galaxy is, the more its light has been redshifted. For the most distant galaxies, essentially all their visible light has been shifted into the infrared. We can detect them with infrared telescopes like the James Webb Space Telescope, but they're completely invisible to optical telescopes and to the human eye. They contribute nothing to the visible brightness of the night sky. Even galaxies at moderate distances contribute less light than we might expect because of redshift. A galaxy that would appear bright and blue if it were nearby might appear faint and red because of its redshift. Not only are its light waves stretched to longer wavelengths, but the energy of each photon is reduced. A photon's energy is inversely proportional to its wavelength, so as the wavelength stretches, the energy decreases. This means that redshifted light carries less energy per photon than the light when it was emitted. There's also a geometric effect at play. As the universe expands, the distance between us and a distant galaxy increases. This means photons are spread over a larger area by the time they reach us, following the inverse square law. Combined with the energy loss from redshift and the rate at which photons arrive, also reduced by cosmic expansion, distant galaxies appear much, much fainter than they would in a non-expanding universe. The expansion rate of the universe, quantified by the Hubble constant, determines how quickly galaxies at various distances are receding from us. Current measurements place the Hubble constant at about 70 kilometers per second per megaparsec, though there's an ongoing controversy in cosmology because different measurement methods give slightly different values. This Hubble tension is an active area of research. Using the Hubble constant, we can calculate recession velocities for galaxies at different distances. A galaxy 500 million light-years away is receding from us at about 10,000 kilometers per second, more than 3% of the speed of light. A galaxy 5 billion light-years away is receding at about 100,000 kilometers per second, 1/3 the speed of light. At the edge of the observable universe, galaxies are receding from us at speeds exceeding the speed of light. This superluminal recession doesn't violate special relativity because these galaxies aren't moving through space faster than light. Instead, the space between us and them is expanding. An analogy might help. Imagine ants walking on a stretching rubber band. Each ant is walking at a modest speed across the rubber surface, but if the rubber is stretching quickly, two ants far apart on the band might be separating faster than either ant can walk. The expansion of space works similarly. For galaxies receding faster than light, the situation becomes even more extreme. Light emitted from these galaxies in our direction is still carried away from us by the expansion of space, at least initially. Only if the photon is close enough to us that local expansion rates are low enough will it ever actually reach us. The most distant regions of the observable universe represent places where photons emitted shortly after the Big Bang have only just now had enough time to overcome the expansion and reach us. The redshift we observe in the universe provides some of the strongest evidence for the Big Bang theory. If the universe is expanding now, it must have been smaller and denser in the past. Run time backward far enough, and you reach a state of extreme density and temperature, the Big Bang singularity. The exact nature of this initial state remains a topic of active research, with quantum theories of gravity needed to describe it, but the expansion itself is firmly established through multiple lines of observational evidence, including redshift. Different types of cosmic objects show consistent redshift patterns, confirming that we're observing a universal expansion of space rather than some other phenomenon. Distant galaxies, quasars, gamma-ray bursts, and Type Ia supernovae all exhibit redshifts consistent with an expanding universe. The cosmic microwave background radiation, which we'll discuss in the next section, also shows exactly the redshift pattern predicted by the Big Bang model. Understanding redshift helps us grasp why space appears so dark despite containing so much light. A substantial fraction of the universe's light has been shifted into wavelengths our eyes can't detect. Ultraviolet light from distant galaxies arrives as infrared. Visible light arrives as thermal radiation. Even within the visible spectrum, light is shifted toward the red end, making distant blue galaxies appear red and faint. The darkness we see is an emptiness. It's space filled with light. Our biology and technology can't directly perceive invisible wavelengths. The future evolution of cosmic redshift is equally fascinating. As the universe continues to expand, and as that expansion accelerates due to dark energy, more and more galaxies will be redshifted beyond detectability. Galaxies currently visible will fade from view as their light is stretched to ever longer wavelengths. In the extremely distant future, intelligent beings in our galaxy looking out at the cosmos will see far fewer galaxies than we see today. The universe will appear darker, emptier, because the light from distant sources will have been redshifted beyond any possible detection. This means we're living in a cosmically special time. We're early enough in the universe's history that we can still see a rich population of galaxies throughout the cosmos. We can trace cosmic history back nearly to the Big Bang itself. We can detect the cosmic microwave background and study the conditions in the early universe. Future civilizations won't have access to all this information. The evidence for the Big Bang and cosmic expansion will gradually be erased by that very expansion, stretched and dimmed until it vanishes beyond any horizon of detectability. The redshift of distant galaxies reminds us that we're looking not just across space but also back through time. The light we see from these galaxies left them billions of years ago, when the universe was younger, denser, hotter, and smaller. The darkness between these cosmic beacons represents the vast distances and times that separate them, distances that continue to grow as space expands and carries these distant realms ever farther from our reach. When we talk about the darkness of space, we're often thinking about the darkness between individual stars or between nearby galaxies. But to truly appreciate the scale of cosmic emptiness, we need to zoom out and look at the large-scale structure of the universe. Here, we encounter some of the most mind-boggling voids imaginable, vast regions hundreds of millions of light-years across where almost nothing exists. The universe, on its largest scales, is organized into a structure cosmologists call the cosmic web. This web consists of galaxy clusters and superclusters connected by filaments of galaxies and dark matter, all surrounding enormous empty regions called cosmic voids. If you could see the distribution of galaxies across billions of light-years, It would resemble a sponge or a foam with dense nodes connected by thin strings and vast empty bubbles between them. These cosmic voids are mind-boggling in their emptiness. A typical void might be 300 million light-years in diameter, larger than the distance from the Milky Way to the Virgo supercluster, which itself contains thousands of galaxies. Within such a void, you might find only a handful of galaxies, or sometimes none at all. The density of matter in a void can be 1/10 or even 1/100th the average density of the universe as a whole. To put this in perspective, the average distance between galaxies in a typical region of space is about 1 or 2 million light-years. In our local neighborhood, the Andromeda Galaxy is about 2.5 million light-years away, but in a cosmic void, you might have to travel 100 million light-years before encountering another galaxy. If you were somehow standing on a planet in a galaxy in the middle of a great void, looking out into space, you would see essentially nothing. The nearest galaxies would be so distant they'd appear as the faintest smudges even in powerful telescopes. One of the most famous cosmic voids is the Boötes void, discovered in 1981 by Robert Kirshner and colleagues. This void is approximately 330 million light-years in diameter and contains only about 60 galaxies within its volume. For comparison, a typical region of space this size would contain several thousand galaxies. The Boötes void has been nicknamed the Great Nothing because of its extreme emptiness. Other notable voids include the giant void in the constellation Canes Venatici, about 1.5 billion light-years in diameter, making it one of the largest known structures in the universe. The KBC void, in which our own galaxy may reside, could be 2 billion light-years across. These structures are so large that light takes hundreds of millions or even billions of years to cross them. How did these enormous empty regions form? The answer lies in the early universe and the process of cosmic structure formation. Shortly after the Big Bang, matter was distributed almost uniformly throughout space, with only tiny fluctuations in density, about 1 part in 100,000. These tiny fluctuations, imprinted on the cosmic microwave background, were the seeds of all cosmic structure. Gravity amplified these initial density variations. Regions that were slightly denser than average had slightly stronger gravity, attracting matter from their surroundings. This made them denser still, increasing their gravity further in a runaway process. Meanwhile, the regions from which matter was being drawn became less dense. Over billions of years, this process created the structure we see today. Dense clusters and filaments of galaxies surrounded by vast, underdense voids. The voids aren't completely empty. They contain some dark matter, some diffuse intergalactic gas, and a few isolated galaxies. But they're extraordinarily sparse compared to the filaments and clusters. The few galaxies that do exist in voids tend to be small, dim, and slow to form stars. They lack the rich environment of gas and neighboring galaxies that stimulate star formation in denser regions. From the standpoint of understanding why space is dark, cosmic voids play a significant role. They occupy the majority of the universe's volume. Even though most galaxies are concentrated in filaments and clusters, most of space lies within or between voids. If you picked a random point in the universe, you'd most likely find yourself in a void, dozens or hundreds of millions of light-years from the nearest significant galaxy. This means that most of space really is dark, not just dark in the sense of lacking a scattering medium, but dark in the sense of lacking light sources. A photon traveling through the middle of a cosmic void might go hundreds of millions of light-years without encountering anything. There's no starlight to be seen, no galaxies visible to the naked eye, just an infinite blackness punctuated by the most distant and faint smudges of galaxies on the void's boundaries. The existence and properties of cosmic voids provide important constraints on cosmological models. They help us understand how matter is distributed on the largest scales, how dark energy affects cosmic expansion, and how structure formation proceeded over cosmic history. Simulations of cosmic evolution must reproduce not just the galaxies and clusters we observe, but also the voids, their sizes, shapes, and distributions. Recent studies have shown that voids are not completely devoid of all structure. They sometimes contain smaller voids within them, creating a hierarchy of emptiness. They also aren't perfectly spherical, but have complex, elongated shapes influenced by the surrounding structure. Voids are dynamic, expanding faster than the average expansion rate of the universe because they contain less matter to slow the expansion through gravity. Some cosmologists have proposed that our galaxy resides within a modest void, sometimes called the KBC void after its discoverers. If true, this would mean we're in a region of below-average density, which could have implications for how we measure cosmic expansion rates and might help resolve the Hubble tension. The idea is somewhat controversial, but it illustrates how even our local region of space might be part of a larger underdense structure. The darkness of cosmic voids is absolute in a way that's hard to comprehend. Even the darkness between stars in our galaxy is lit by the diffuse glow of distant stars and the faint light of the Milky Way itself. But in the heart of a cosmic void, there's no Milky Way, no nearby galaxies, no appreciable starlight from any direction. The nearest sources of light are so far away that even their collective glow would be imperceptible. Imagine being on a planet in a galaxy at the center of the Bootes void. Looking up at your night sky, you would see perhaps a few dozen extremely faint smudges. Distant galaxies on the void's boundaries, each one hundreds of millions of light years away. No Milky Way band crosses your sky, no Andromeda galaxy provides a companion. Just darkness and a few barely visible patches of light. It would be a profoundly lonely view of the cosmos, and it would give you a very different impression of the universe than we have from our location in a relatively dense region. Yet even in these voids, space isn't truly empty. Quantum field theory tells us that the vacuum of space is seething with quantum fluctuations, virtual particles popping in and out of existence, zero-point energy filling every cubic centimeter. Dark energy, whatever its nature, permeates the voids just as it does the rest of space. The fabric of space-time itself is present, curved by the small amount of matter and energy the void contains. The cosmic voids also illustrate the heterogeneous nature of the universe on large scales. Space isn't uniformly filled with matter and light. Instead, it's wildly uneven, with most matter concentrated in a relatively small fraction of the volume, and most of the volume occupied by near emptiness. This unevenness contributes significantly to the darkness we observe. We happen to live in a relatively dense region, but even from here, much of what we see when we look out into space is the darkness of voids rather than the light of galaxies. Understanding cosmic voids helps complete our picture of why space is dark. It's not just that individual photons travel in straight lines without scattering. It's not just that the universe has a finite age and light has only had finite time to reach us. It's not just that expansion redshifts distant light beyond visibility. It's also that most of space, by volume, is genuinely far from any significant light sources. The universe is lumpy, clumpy, web-like, and most of that structure is empty space between the luminous parts. When we discuss the light-filling space, we must address one of the most important forms of electromagnetic radiation permeating the cosmos, the cosmic microwave background, or CMB. This radiation is the afterglow of the Big Bang itself, a relic from the early universe that fills all of space uniformly. Yet despite being everywhere, this light contributes nothing to the visible brightness of the sky. Understanding why tells us a great deal about both the CMB and the nature of cosmic darkness. The cosmic microwave background dates back to approximately 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that matter existed as a plasma, a soup of free electrons and atomic nuclei with no neutral atoms. In this plasma state, photons couldn't travel far before being scattered by free electrons. The universe was opaque, foggy with constant interactions between light and matter. As the universe expanded, it cooled. At a temperature of about 3000 Kelvin, conditions changed dramatically. Electrons combined with protons to form neutral hydrogen atoms in a process called recombination. Once most electrons were bound into atoms, photons could suddenly travel freely through space without constantly scattering. The universe became transparent. The photons that were freed at this moment have been traveling through space ever since, carrying with them information about the conditions in the early universe. When these photons were released, they had a temperature of about 3000 Kelvin, corresponding to a warm orange glow similar to the heating element of an electric stove. But the universe has expanded tremendously since then. Space has stretched by a factor of about 1,100, and this expansion has stretched the wavelengths of these ancient photons along with it. Today, those photons have cooled to a temperature of just 2.725 Kelvin, just barely above absolute zero. This temperature corresponds to microwave radiation, which is why we call it the cosmic microwave background. The peak wavelength is about 1.9 millimeters, firmly in the microwave range of the electromagnetic spectrum. This is far outside the range of human vision. Our eyes evolved to detect wavelengths between about 390 and 700 nanometers. Microwaves have wavelengths thousands of times longer. We're biologically blind to the CMB. The CMB is remarkably uniform across the sky. In every direction you look, you encounter this microwave radiation at almost exactly the same temperature. The variations are tiny, only about 1 part in 100,000. These minute temperature differences, first detected by the COBE satellite in 1992 and mapped in exquisite detail by the WMAP and Planck satellites, correspond to the slight density variations in the early universe that eventually grew into galaxies, clusters, and cosmic structure. Despite its uniformity and low temperature, the CMB contains an enormous amount of energy. There are approximately 400 CMB photons per cubic centimeter of space, compared to about 0.0001 visible light photons per cubic centimeter from stars. The CMB photons vastly outnumber photons from all other sources. In terms of photon count, the CMB dominates the universe, yet we don't see it because of its wavelength. If we could see microwaves the way we see visible light, the entire sky would glow with a nearly uniform brightness. There would be no darkness, just a faint orange-red glow from every direction. The temperature variations would appear as slightly brighter and darker patches, creating a mottled pattern across the sky. But these variations would be subtle, a difference of about 100 millionth of a degree, barely perceptible even if we could see them. The CMB's invisibility to our eyes is a direct consequence of our evolutionary history. Life on Earth evolved under the light of the sun, which emits most of its energy in the visible range. Our eyes adapted to detect these wavelengths because they were useful for survival, seeing predators, finding food, recognizing other humans. There was no evolutionary advantage to detecting microwaves, so we never developed that ability. However, we can detect the CMB with radio telescopes and specialized instruments. These observations have revolutionized our understanding of cosmology. By analyzing the precise temperature and polarization patterns in the CMB, cosmologists have measured the age of the universe, its composition, its geometry, and the history of cosmic expansion with unprecedented precision. The CMB is one of the most important sources of information we have about the cosmos. The story of the CMB's discovery is one of the great tales of 20th century science. In 1964, Arno Penzias and Robert Wilson at Bell Labs were working with a sensitive microwave antenna, trying to eliminate all sources of noise. They kept detecting a persistent background hum from all directions in the sky at a temperature of about 3.5 Kelvin. They even cleaned out pigeon droppings from the antenna, thinking the birds might be the source of the noise. But the signal remained. Meanwhile, a team of physicists at Princeton, led by Robert Dicke, had predicted that if the Big Bang theory was correct, there should be a background of microwave radiation filling the universe, a remnant from the early hot phase. When Dicke's team learned of Penzias and Wilson's mystery signal, they realized immediately what it was. The cosmic microwave background had been discovered accidentally. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery. The CMB provides powerful evidence for the Big Bang theory and against alternative cosmological models like the steady-state theory. Only a universe that was once hot and dense, then expanded and cooled, would produce the specific thermal spectrum we observe. The CMB's near-perfect uniformity also tells us that the early universe was remarkably homogeneous, with only tiny fluctuations that would later grow into cosmic structure. One fascinating aspect of the CMB is that it has a dipole pattern. It's slightly warmer in one direction and cooler in the opposite direction. This isn't a property of the CMB itself, but rather an effect of our motion through space. Our solar system is moving at about 370 kilometers per second relative to the CMB rest frame, and this motion creates a Doppler effect. The CMB appears blue-shifted, warmer, in the direction we're moving toward, and red-shifted, cooler, in the direction we're moving from. By measuring this dipole precisely, we can determine our velocity through space relative to the cosmic rest frame. The CMB also contains information about the composition of the universe. By analyzing its spectrum and temperature variations in detail, cosmologists have determined that the universe consists of about 5% ordinary matter, atoms, 27% dark matter, and 68% dark energy. These measurements, combined with other observations, paint a picture of a universe dominated by mysterious components we don't yet fully understand. From the perspective of understanding cosmic darkness, the CMB represents an enormous amount of light that's invisible to us because it's been redshifted out of the visible range. If we could see microwaves, or if the universe were younger, so the CMB was still in the visible range, space wouldn't appear dark at all. It would glow uniformly. The darkness we perceive is partly because we lack the biological equipment to detect the most abundant form of electromagnetic radiation in the universe. The CMB will continue to be a subject of intensive study for decades to come. Future experiments will measure its polarization patterns in even greater detail, potentially detecting the signature of gravitational waves from the earliest moments of the universe. These measurements could provide evidence for cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. The ancient light from the CMB still has secrets to reveal about the birth and evolution of our cosmos. When we say that space is full of light, we're not just talking about visible light from stars and galaxies. The electromagnetic spectrum extends far beyond the narrow range our eyes can detect, and space is filled with radiation across this entire spectrum. Much of the darkness we perceive is actually awash with invisible forms of electromagnetic radiation that our biology simply cannot sense. Let's start with infrared radiation, which has wavelengths longer than visible red light, but shorter than microwaves. Infrared fills space in abundance. Every object with a temperature above absolute zero emits infrared radiation, with the wavelength and intensity depending on the temperature. Warm objects like planets, asteroids, comets, and dust clouds all glow brightly in infrared, even though they emit little or no visible light. Stars also produce copious amounts of infrared radiation, especially cool red dwarf stars whose peak emission lies in the infrared range. Some of the most luminous objects in the universe, like certain galaxies, undergoing intense star formation, emit most of their energy in the infrared. This happens because the starlight is absorbed by dust, which heats up and re-radiates the energy as infrared light. To infrared-sensitive eyes, space would appear much brighter than it does in visible light, filled with glowing warm objects everywhere. The James Webb Space Telescope, launched in December 2021, is optimized for infrared observations. Its images have revealed a universe teeming with previously unseen objects, distant galaxies whose light has been redshifted into the infrared, cold dust clouds where stars are forming, the atmospheres of exoplanets, and stellar populations hidden by dust. JWST operates at wavelengths from about 0.6 to 28.5 microns, covering the near and mid-infrared ranges. At even longer wavelengths, in the far infrared and submillimeter ranges, we find radiation from cool dust and the cosmic microwave background. Specialized telescopes like the Herschel Space Observatory and the Atacama Large Millimeter Array observe in these wavelengths, revealing yet more hidden aspects of the cosmos. Cold molecular clouds, regions where stars will someday form, shine in these wavelengths despite being dark and opaque at visible wavelengths. Moving in the other direction on the electromagnetic spectrum, we encounter ultraviolet radiation, which has shorter wavelengths than visible violet light. Hot young stars are prolific ultraviolet emitters. These massive, bright blue stars burn at temperatures of 20,000 to 50,000 Kelvin or more, producing intense UV radiation. The ultraviolet sky, if we could see it, would be dominated by these hot young stars and by regions of ionized hydrogen gas heated by their radiation. Ultraviolet observations have to be made from space because Earth's atmosphere absorbs most UV radiation, fortunately for life on Earth, since intense UV can damage DNA and biological molecules. Satellites like the International Ultraviolet Explorer, the Hubble Space Telescope, which observes in UV as well as visible and near-infrared, and the Galaxy Evolution Explorer, JLEX, have mapped the ultraviolet sky, revealing active galactic nuclei, hot stellar populations, and regions of active star formation. Beyond ultraviolet lies the X-ray portion of the spectrum. X-rays are produced by extremely hot plasma, typically millions of Kelvin or hotter, and by high-energy processes like matter falling into black holes or neutron stars. The X-ray sky is dominated by different sources than the visible sky. Instead of seeing ordinary stars, X-ray telescopes see neutron stars, black holes, supernova remnants, hot gas in galaxy clusters, and active galactic nuclei where supermassive black holes are feeding. Our Sun produces X-rays from its corona, the outermost layer of its atmosphere where temperatures reach millions of Kelvin. Solar flares produce intense bursts of X-rays. Other stars, particularly young active stars and close binary systems, also emit X-rays. The hot gas between galaxies in clusters, heated to tens of millions of Kelvin, glows brightly in X-rays, making galaxy clusters prominent X-ray sources, even though they're nearly invisible in ordinary light. X-ray astronomy from space began in the 1960s and has expanded dramatically with missions like the Chandra X-ray Observatory, XMM Newton, and NuSTAR. These telescopes have revealed a violent, energetic universe invisible to optical telescopes. Stellar mass black holes feeding from companion stars produce X-ray binaries. Neutron stars spinning hundreds of times per second create X-ray pulsars. Supermassive black holes at the centers of galaxies power quasars and active galactic nuclei that can outshine entire galaxies in X-rays. At the highest energies, we find gamma rays, the most energetic form of electromagnetic radiation. Gamma rays are produced by radioactive decay, by matter-antimatter annihilation, and by ultra-high energy astrophysical processes. Gamma ray bursts, the most luminous explosions in the universe, release as much energy in seconds as the Sun will emit in its entire 10 billion year lifetime, almost all of it as gamma rays. Pulsars, rotating neutron stars with intense magnetic fields, can produce beams of gamma rays. When these beams sweep across Earth, we detect them as pulsing gamma ray sources. The Fermi Gamma Ray Space Telescope has catalogued thousands of gamma ray sources across the sky, most of them active galactic nuclei where supermassive black holes are accelerating particles to near light speed. Even our Milky Way glows in gamma rays. The galactic center emits gamma rays from unknown sources, possibly dark matter annihilation, though more conventional explanations involving pulsars and cosmic rays also exist. The entire galactic plane shows a diffuse gamma ray glow from cosmic rays, high-energy particles, interacting with interstellar gas and starlight. All this invisible radiation, infrared, ultraviolet, X-rays, gamma rays, fills space constantly. From every direction, photons in these wavelengths are streaming through space, carrying information about the cosmos. But our eyes detect none of it. We're biologically limited to a tiny slice of the electromagnetic spectrum, the slice where the Sun emits most of its energy and Earth's atmosphere is relatively transparent. This biological limitation means we're missing most of the action. The universe is far more active, violent, and energetic at invisible wavelengths than at visible wavelengths. If we could see X-rays, the sky would be dominated by black holes and hot gas. If we could see infrared, we'd see warm dust clouds everywhere. If we could see gamma rays, we'd witness the most powerful explosions in the universe. But we see none of this naturally, only the relatively calm, visible light universe of stars and galaxies. Recent discoveries have revealed an additional puzzle about cosmic light. The New Horizons spacecraft, which flew past Pluto in 2015 and continues into the outer solar system, has made observations of the cosmic optical background, the total visible light from all sources in the universe. Working from the outer solar system, far from the sun and planets, where light from the solar system is minimized, New Horizons has detected that space is about twice as bright in visible light as we can account for from known sources. This suggests there's an additional component of visible light we haven't identified. Possible explanations include previously uncounted dwarf galaxies, light scattered by interplanetary or interstellar dust we haven't detected, or some other diffuse source. The existence of this unexplained light doesn't make space appear bright to the eye. It's still far too faint for that, but it indicates our census of light sources is incomplete. The hidden light at all wavelengths plays crucial roles in cosmic processes. Infrared light from dust clouds tells us where stars are forming. Ultraviolet light from hot stars ionizes surrounding gas, creating glowing nebulae. X-rays from accretion onto black holes and neutron stars trace the most extreme gravity in the universe. Gamma rays signal the deaths of massive stars and the mergers of neutron stars. Each wavelength regime provides unique information about cosmic phenomena. From the perspective of understanding why space appears dark, the abundance of invisible light is revealing. Space isn't dark in any absolute sense. It's full of electromagnetic radiation at all wavelengths. But space appears dark to human eyes because we can only detect a tiny fraction of this radiation, and even within the visible spectrum, most of the photons streaming through any given region of space aren't traveling in our direction. We see only the tiniest sample of the light that's actually present. If we had evolved with eyes sensitive to a different part of the spectrum, our perception of the cosmos would be radically different. Infrared eyes would see a warmer, glowier universe. Ultraviolet eyes would emphasize hot young stars and ionized gas. X-ray eyes would see a violent universe of black holes and hot plasma. The darkness we perceive is as much a property of our biology as it is of the universe itself. Modern astronomy has overcome our biological limitations by building instruments that can detect radiation across the entire electromagnetic spectrum. Together, these instruments give us a complete picture of the cosmos, revealing all the hidden light our eyes miss. But when we simply look up at the night sky with our eyes alone, we see only darkness, not because space lacks light, but because we lack the ability to see most of the light that's there. One of the most striking aspects of the question, why is space dark, is that there are so many stars. The numbers are almost incomprehensible. Current estimates suggest there are between 200 billion trillion and 200 sextillion stars in the observable universe. That's a 2 followed by 23 or 24 zeros. To write it out, 200 trillion stars, possibly much more. Let's try to grasp this number. If you tried to count all these stars, giving each one just 1 second, it would take you about 6 trillion years, roughly 400 times the current age of the universe. If every person who ever lived devoted their entire life to counting, working every second without pause, humanity still wouldn't have finished counting. The number of stars exceeds the number of grains of sand on all of Earth's beaches, perhaps by a large margin depending on how you count. Each of these stars is a massive nuclear fusion reactor, converting hydrogen into helium and releasing tremendous amounts of energy in the process. Our Sun, a fairly average star, produces about 3.8 times 10 to the 26th watts of power continuously. It's been doing this for about 4.6 billion years and will continue for another 5 billion years or so. Over its lifetime, it will convert about 100 Earth masses of hydrogen into helium, converting roughly 0.7% of that mass into pure energy via Einstein's famous equation E equals mc squared. Many stars are far more luminous than the Sun. Blue supergiants like Rigel in the constellation Orion can be 100,000 times more luminous. The most massive stars known, like R136a1 in the Large Magellanic Cloud, may be several million times more luminous than the Sun. These stellar powerhouses pour out energy at rates that make our Sun look dim by comparison, and there are billions of them across the universe. Yet despite this tremendous abundance of light-producing stars, despite the unimaginable energy they collectively pour into space every second, the night sky remains dark. The fundamental reason is simple. The stars are incredibly far apart compared to their size. Space is aptly named. It's mostly empty space with occasional tiny dots of matter and light. Consider the distances. Our nearest stellar neighbor, Proxima Centauri, is about 4.24 light-years away, or roughly 40 trillion kilometers. Light, traveling at 300,000 kilometers per second, takes more than 4 years to cross this distance. The Sun has a diameter of about 1.4 million kilometers. This means that the distance to the nearest star is about 30 million times the Sun's diameter. To visualize this, imagine shrinking the Sun down to the size of a basketball. On this scale, Earth would be a small peppercorn about 26 meters away. Neptune, the outermost major planet, would be about 800 meters away. And Proxima Centauri, our nearest stellar neighbor, would be another basketball 6,800 kilometers away, roughly the distance from New York to Rome. That's how much empty space lies between stars. This vast emptiness means that even though stars are producing enormous amounts of light, the light from any given star is spread over an increasingly large area as it travels through space. By the time it travels the distance to a neighboring star, it's spread so thin that it contributes almost nothing to illuminating that distance. And most of space is much farther from any star than the nearest neighbor distance. The inverse square law of light governs this spreading. If you're 1 meter from a light source and you move to 2 meters away, the light is spread over 4 times the area, so the brightness decreases to 1/4. At 3 meters, brightness is 1/9. At 10 meters, 1/100th. At 100 meters, 1/10,000th. The decrease is dramatic and relentless. For starlight, this means that brightness falls off precipitously with distance. Even nearby stars appear as mere pinpoints, not bright disks, because they're so far away. The Sun appears as a disk only because it's relatively close, about 150 million kilometers, but even Alpha Centauri, one of the brightest stars in our sky, and one of the closest, appears only as a bright point. If you were standing on a planet around Alpha Centauri, looking back at our Sun, it would appear as merely a bright star, not the blazing disk we see from Earth. Let's consider the total amount of starlight filling space in our galaxy. The Milky Way contains between 100 billion and 400 billion stars. These stars produce a tremendous total amount of light. Yet if you're in interstellar space, far from any particular star, the combined light from all these billions of stars amounts to very little. The nearest stars dominate the light you receive, and even they provide only faint illumination. Measurements from spacecraft in the outer solar system, far from the Sun's glare, have quantified this starlight. In deep space in our galaxy, away from the Sun but in a typical location with average stellar density, the combined light from all stars would provide illumination roughly equivalent to a clear moonless night on Earth. Faint, but enough to make out basic shapes if your eyes were adapted. That's the contribution from hundreds of billions of stars combined. This seems counterintuitive. How can so many stars produce so little light? The answer lies in the inverse square law combined with the distances involved. Yes, there are hundreds of billions of stars, but they're spread across a galaxy about 100,000 light-years in diameter. Most of them are tens of thousands of light-years away. At such distances, even luminous stars contribute almost nothing to the local light level. In intergalactic space, the situation is even more extreme. The nearest large galaxy to the Milky Way is Andromeda, about 2.5 million light-years away. It contains about 1 trillion stars, yet from Earth, Andromeda appears as a faint, fuzzy patch, visible only in dark skies, subtending about 6 times the apparent diameter of the Moon. All trillion of those stars combined don't produce as much apparent brightness as a single modest star in our own galaxy. At the scale of galaxy clusters and superclusters, distances become truly cosmic. The Virgo cluster, the nearest large cluster of galaxies, is about 54 million light-years away and contains about 2,000 galaxies. Collectively, these galaxies contain trillions of stars. Yet from Earth, even in the darkest skies with the most sensitive instruments, most of these galaxies are barely detectable. The light from trillions of stars has spread out so much over 54 million light-years that it's become vanishingly faint. The most distant galaxies visible to the Hubble and James Webb Space Telescopes are billions of light-years away, at redshifts where the light has been traveling for most of cosmic history. These galaxies contain billions or trillions of stars, but we detect them only as faint smudges, requiring hours or days of telescope exposure time to image. The light from all those stars, spread over billions of light-years of distance and redshifted by cosmic expansion, arrives at Earth at a rate of only a few photons per second into our telescopes. This dilution of light by distance is one of the fundamental reasons space appears dark. No matter how many stars exist, no matter how much energy they produce, the light gets spread so thin over cosmic distances that most of space remains dark. Each star is an intense source of light locally, but its influence extends only a modest distance before fading to insignificance. There's also the matter of what fraction of space stars actually occupy. A star is typically a few 100,000 to a few million kilometers in diameter. The distance between stars is typically a few light-years to tens of light-years. This means that in any random volume of interstellar space, the fraction occupied by actual stellar material is extraordinarily tiny, perhaps 1 part in 10 to the 15 or 10 to the 18. To put this differently, if you selected a random location in the Milky Way, the probability that you'd be inside a star is essentially zero. You'd almost certainly be in the empty space between stars. And in that location, the light from the nearest stars would be spread thin by distance. You'd see stars as points of light in the distance, but the space around you would be dark. The situation in intergalactic space is even more extreme. Here, the nearest stars might be millions of light-years away in the nearest galaxies. The light reaching any point in intergalactic space from all sources combined would be incredibly faint, far less than the combined starlight in interstellar space within a galaxy. An observer in deep intergalactic space, in a cosmic void between galaxy clusters, would see almost complete darkness, perhaps a few extremely faint smudges marking the locations of distant galaxy clusters and nothing else. The numbers, as vast as they are, work against brightness rather than for it. 200 sextillion stars sounds like it should light up the universe brilliantly. But spread across the observable universe's diameter of 93 billion light-years, distributed in filaments and clusters with vast voids between, these stars end up being so separated by distance that their collective light, even in aggregate, fails to illuminate most of space. Understanding the distribution and density of stars helps us grasp why Olbers's paradox isn't actually paradoxical once we know the true structure of the universe. The paradox assumed a uniform distribution of stars extending infinitely. But stars aren't uniformly distributed. They're clustered in galaxies, galaxies are clustered in groups and clusters, and these clusters are arranged in filaments around enormous voids. And most importantly, we can only see a finite number of stars within our cosmic horizon, and most of those we can see are tremendously far away and dimmed by distance. The sheer number of stars is staggering, awe-inspiring, humbling. 200 billion trillion stars, each one a sun, each one potentially with planets, each one burning with nuclear fire. Yet the spaces between them are so vast, the dilution of their light by distance so severe that the dominant feature of the cosmos remains not light, but darkness. The stars are islands of light in an ocean of black, and the ocean is far, far larger than the islands. We've explored many individual factors that contribute to the darkness of space: the lack of scattering medium in vacuum, the finite age of the universe, cosmic expansion and redshift, the existence of vast cosmic voids, the invisibility of most electromagnetic radiation to human eyes, and the tremendous distances between stars and galaxies. Now let's bring all these factors together to form a complete picture of why space is black despite being full of light. First and foremost, light in a vacuum travels in straight lines without scattering. This is perhaps the most fundamental reason for the darkness of space. On Earth, we're accustomed to diffuse illumination because our atmosphere scatters sunlight in all directions, creating a bright sky even when we're not looking directly at the sun. But in space, there's no atmosphere, no medium to scatter light. Photons travel directly from their source to any object they hit, and space between sources and objects remains dark because there's nothing for the light to scatter off of. This explains why astronauts see a black sky even in direct sunlight, why the moon's sky is black even during lunar day, and why spacecraft cameras always show stars as points of light against perfect blackness. The absence of scattering means space itself is invisible. We only see objects that emit or reflect light, not the space between them. Second, the universe has a finite age of approximately 13.8 billion years. This places a fundamental limit on how much of the universe we can observe. Light travels at a finite speed, so we can only see light from objects whose light has had time to reach us. Beyond our cosmic horizon, countless stars and galaxies may exist, but their light hasn't reached us yet. They don't contribute to the brightness of our sky. This finite age directly resolves Olbers's paradox. If the universe were infinite in age, with stars having shone forever, the sky should be infinitely bright. But with a finite age, only a finite number of photons from a finite number of sources have had the opportunity to reach any given point in space. The darkness of space is evidence for the Big Bang, proof that our universe had a beginning. Third, the universe is expanding, and this expansion stretches the wavelength of light as it travels through space. Distant galaxies are receding from us at speeds proportional to their distance, with the most distant galaxies receding faster than the speed of light due to the expansion of space itself. This expansion creates cosmological redshift, which shifts light from distant sources to longer wavelengths. Many galaxies that would appear bright and blue if they were nearby appear faint and red, or are shifted completely out of the visible spectrum into the infrared. The most distant galaxies we can detect have had their visible light shifted into infrared or even microwave wavelengths. This redshift dramatically reduces the contribution of distant sources to the visible brightness of space. Much of the universe's light has been rendered invisible by expansion. Fourth, the universe contains enormous cosmic voids, vast regions hundreds of millions of light years across, where galaxy density is far below average. These voids occupy most of the universe's volume. A random point in space is most likely to be in a void, far from any significant light source. Even in regions where galaxies are present, they're organized into filaments and clusters with large empty spaces between them. This means that most of space, by volume, is genuinely distant from any bright light sources. In deep intergalactic space, particularly within voids, the nearest galaxies may be hundreds of millions of light years away. The light from such distant sources, diminished by the inverse square law and redshifted by expansion, contributes almost nothing to local brightness. The universe's large-scale structure ensures that emptiness dominates over luminosity. Fifth, our eyes detect only a tiny fraction of the electromagnetic spectrum. The universe is filled with radiation at all wavelengths: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The cosmic microwave background alone consists of about 400 photons per cubic centimeter, vastly outnumbering visible light photons. But our eyes evolved to see only the narrow range of wavelengths from about 390 to 700 nanometers. All the infrared light from warm dust and cool stars, all the ultraviolet light from hot young stars, all the X-rays from black holes and hot gas, all the gamma rays from the most energetic processes, we're blind to all of it. If we could see the full electromagnetic spectrum, space would appear much brighter. But we can't, and our perception of darkness is partly a consequence of our biological limitations. Sixth, stars and galaxies, though incredibly numerous, are separated by vast distances. The inverse square law ensures that light diminishes rapidly with distance. Even the nearest stars are so far away that they appear as mere points. Most stars in our galaxy are thousands or tens of thousands of light years away and contribute almost nothing to local illumination. Galaxies beyond our own are millions or billions of light years distant, rendering them faint or invisible despite containing billions or trillions of stars. The sheer scale of cosmic distances means that even 200 billion trillion stars spread across the observable universe don't succeed in lighting up space. They're like scattered candles in a vast, dark cathedral, each candle bright locally, but unable to illuminate the whole space because the space is so much larger than the range of their light. Seventh, energy conservation plays a role. The total amount of energy released by stars since the Big Bang is finite. Stars convert mass into energy through fusion, but at any given moment, only a certain amount of starlight is traveling through space. This light is spread over the enormous volume of the universe, and much of it has been redshifted to longer wavelengths or absorbed by dust and gas. The energy density of starlight in space is actually quite low. Calculations of the cosmic optical background, the total visible light from all sources, show that even accounting for all stars and galaxies, the background brightness is only about equivalent to the light from a few hundred stars like the sun spread across the entire sky. This isn't bright enough to appear as anything other than darkness to the human eye. You need concentrated sources, individual stars and galaxies, to see anything at all. Eighth, dust and gas in space absorb and scatter some light, particularly in galactic disks and in dense molecular clouds. While this isn't the primary reason space is dark, as we've discussed, the tired light explanation fails for Olbers's paradox, it does play a minor role in dimming light from very distant sources within galaxies and in obscured regions. However, the dust itself re-radiates absorbed energy as infrared light, so this process doesn't eliminate light, but rather transforms it to longer wavelengths. All these factors work together synergistically. It's not just one thing that makes space dark, it's the combination of many factors, each one contributing to the overall darkness we observe. The lack of scattering combined with finite light travel time, combined with redshift, combined with cosmic voids, combined with our limited vision, combined with vast distances, all these together ensure that space appears profoundly black despite being permeated by light. Modern cosmology has thus provided a complete answer to a question that puzzled humanity for centuries. Space is dark not because it lacks light, but because of the fundamental nature of the universe, its vacuum structure, its finite age, its expansion, its vast scale, and our own biological limitations. The darkness is not an absence, but a consequence, a natural outcome of how the universe works. This understanding represents a triumph of scientific inquiry. It required developments in physics, understanding light and electromagnetism, astronomy, mapping cosmic structure, cosmology, understanding the universe's evolution, and technology, building instruments to detect invisible radiation and measure cosmic distances. The darkness of space, once a simple observation, has become a window into the deepest workings of reality. The darkness also has philosophical implications. It reminds us of the universe's vastness, of the tremendous scales of space and time that dwarf human experience. It demonstrates that our intuitions, developed in the context of Earth's surface and atmosphere, often fail when applied to cosmic scales. The universe is stranger, larger, older, and more complex than our everyday experience suggests. And yet, this darkness is not empty or meaningless. It's filled with photons at all wavelengths, carrying information about stars, galaxies, and cosmic history. It's structured by the expansion of space, shaped by gravity, permeated by dark matter and dark energy. The darkness between the stars is as much a part of the universe as the stars themselves, and understanding it has led us to profound insights about existence itself. We began this journey with a simple observation. Space is black, deeply and overwhelmingly black, despite being filled with hundreds of billions of trillions of stars. This apparent contradiction, darkness amid abundance, has been our guide through some of the most profound concepts in modern science. We've discovered that the darkness of space isn't a mystery requiring a single clever explanation. Instead, it's the result of multiple interlocking factors, each one a fundamental aspect of how our universe works. The vacuum of space prevents light from scattering. The universe's finite age limits what we can see. Cosmic expansion redshifts distant light beyond visibility. Vast cosmic voids occupy most of space's volume. Our eyes detect only a narrow slice of the electromagnetic spectrum, and the immense distances between stars ensure that light grows faint before traveling far. Each of these factors tells us something important about the cosmos. The lack of scattering in vacuum reveals space's emptiness, the fact that even between galaxies, matter is so sparse that photons can travel for billions of light years without encountering a single atom. This emptiness is itself profound. Space is the closest thing nature provides to absolute nothingness, yet it's not quite nothing. It's a quantum foam seething with virtual particles, permeated by fields and dark energy, structured by the curvature of space-time. The finite age of the universe speaks to beginnings and endings, to the fact that our cosmos hasn't always existed and will continue to evolve into a future we can only imagine. The Big Bang, that moment, 13.8 billion years ago, when space and time themselves came into existence, set the initial conditions for everything we see. The darkness of the night sky is evidence for this beginning, proof that the universe hasn't been producing light forever. Cosmic expansion and redshift reveal a universe in motion, growing larger with each passing moment, carrying galaxies away from each other and stretching the very fabric of space. This expansion, driven by dark energy we don't yet understand, ensures that most of the light in the universe has been shifted to wavelengths we can't see. In a very real sense, the universe is hiding most of its light from us, rendering it invisible through expansion alone. The cosmic voids remind us that the universe is not uniform, but structured, web-like, with matter concentrated in filaments and clusters surrounding enormous emptinesses. These voids, hundreds of millions of light years across, are regions where darkness truly dominates, where an observer would see almost nothing, just a few faint smudges marking distant galaxy clusters. Most of space lies in or between these voids, far from the light of stars and galaxies. Our biological limitations teach us humility. We evolved on a planet bathed in sunlight, and our eyes adapted to see the wavelengths where that light is strongest. But the universe speaks in many wavelengths, most of which we cannot naturally perceive. The microwave glow of the Big Bang's afterglow, the infrared warmth of dust and cool stars, the ultraviolet blaze of hot young stars, the X-ray fury of black holes, all these are invisible to us. We've overcome these limitations through technology, but our direct experience remains limited to a tiny slice of reality. The distances between stars and galaxies, those vast gulfs measured in light years and megaparsecs, show us the universe's immense scale. Even traveling at light speed, the fastest possible speed, it takes years to reach the nearest stars and billions of years to traverse the observable universe. In a very real sense, we're isolated by distance, cut off from most of the universe by the sheer scale of space and the finite speed at which information can travel. Bringing all these insights together, we arrive at a profound realization. The darkness of space is not a failure or an absence. It's a natural consequence of living in an expanding universe with a finite age, in a cosmos where light travels at a fixed speed through a near-perfect vacuum, in a universe structured on scales that boggle the mind. The darkness is, in its own way, as meaningful as the light. It tells us about the universe's history, structure, and fundamental nature. When you look up at the night sky and see stars scattered across blackness, you're witnessing multiple cosmic truths simultaneously. You're seeing the evidence for the Big Bang in the darkness between stars. You're observing the structure of space itself in the way starlight travels to your eyes. You're experiencing the limitations of human perception, seeing only the tiniest fraction of the light that's actually present. You're feeling the scale of cosmic distances that separate the islands of light. There's something deeply moving about this. The darkness we've explored isn't empty or meaningless. It's full of history, structure, and information. It's shaped by forces and processes operating on scales from the quantum to the cosmic. Every photon that enters your eye when you look at a star has traveled across space. Perhaps for hundreds or thousands or millions of years, carrying information about where it came from and what it passed through. The darkness between those photons, the blackness of space, is equally meaningful. It represents all the light that didn't make the journey to your eye, light heading in other directions, light that hasn't arrived yet, light shifted to invisible wavelengths, light from sources beyond our horizon. The darkness is, paradoxically, a kind of information itself, telling us about what's not there, what's too far, what's been hidden by expansion or time or distance. Modern science has given us the tools to understand this darkness, to measure it, to explain it, to appreciate it. We can detect light at wavelengths our eyes can't see, mapping the universe in infrared, ultraviolet, X-rays, and gamma rays. We can measure distances to galaxies billions of light years away, determining how long their light has been traveling and how much space has expanded during that journey. We can detect the cosmic microwave background, hearing the echo of the Big Bang itself. Yet for all our knowledge, for all our sophisticated instruments and elegant theories, the fundamental experience remains the same as it was for our ancestors thousands of years ago. We look up and we see darkness punctuated by light. We see the cosmos laid out before us, beautiful and mysterious and vast. The science hasn't diminished the wonder. If anything, it has enhanced it by revealing how much more there is to the darkness than meets the eye. The future of our understanding is bright, even if space remains dark. New telescopes, like the James Webb Space Telescope, now operating and future missions planned for the coming decades, will peer even deeper into space and time, finding ever more distant galaxies and detecting ever fainter sources of light. We'll map cosmic structure in greater detail, measure the expansion rate more precisely, perhaps finally understand the nature of dark matter and dark energy. But no matter how much we learn, the darkness will remain. It's not a problem to be solved, but a fundamental feature of the cosmos. Space is dark because that's how the universe is. The darkness is as essential to the cosmic story as the light, as necessary to the structure of reality as stars and galaxies and planets. So the next time you find yourself under a dark sky, away from city lights, looking up at the stars, remember what you're seeing. You're witnessing the consequences of the Big Bang, the expansion of space, the vast emptiness of the universe, the limitation of human vision, and the immense distances that separate cosmic structures. You're seeing darkness that's full of invisible light, emptiness that's structured and meaningful, blackness that tells a story about the nature of existence itself. The darkness of space is one of the universe's greatest lessons. It teaches us about scale and time, about light and matter, about expansion and distance. It shows us that reality is stranger and more subtle than our everyday experience suggests. It reminds us that we're part of something vast and ancient and ongoing, a cosmos that began billions of years ago and will continue for billions or trillions more years. And in a poetic sense, the darkness also gives meaning to the light. Without the darkness, individual stars wouldn't stand out. Without the blackness of space, we wouldn't see the structure of galaxies, the colors of nebulae, the subtle differences between stellar types. The darkness is the canvas on which the universe paints its portrait in light. It's the silence that makes the cosmic symphony audible. Every civilization that has looked up at the night sky has been shaped by what they saw there. Ancient peoples created myths about the stars, connecting them into constellations and weaving stories to explain their presence and movements. Those stories helped humans understand their place in the cosmos, creating meaning from the patterns of light and dark above them. As our understanding grew, as we moved from mythology to astronomy to astrophysics, our appreciation deepened. We learned that those points of light were other suns, that they were organized into vast galaxies, that the universe itself was far larger and older than anyone had imagined. Each discovery expanded our cosmic perspective. Each insight revealed new layers of complexity and beauty. The darkness played a crucial role in this journey of discovery. It was the darkness of the night sky that prompted Olbers to formulate his paradox. It was the darkness between stars that helped astronomers realize how vast space truly is. It was the darkness in deep space observations that revealed the acceleration of cosmic expansion. The darkness has been a key teacher guiding us toward deeper truths about reality. In many ways, we're living in a golden age of understanding cosmic darkness. We have instruments that can detect light across the entire electromagnetic spectrum. We have theories that explain cosmic expansion, structure formation, and the evolution of galaxies. We have measurements of cosmic distances, ages, and compositions with unprecedented precision. We know more about why space is dark than any previous generation. Yet, mysteries remain. Dark matter, which makes up most of the matter in the universe, is still poorly understood. We detect its gravitational effects, but don't know what it's made of. Dark energy, which drives the acceleration of cosmic expansion, is even more mysterious. It seems to be a property of space itself, but its nature remains unknown. These dark components of the universe, dark matter and dark energy, together constitute about 95% of the universe's total mass-energy content. There's a certain appropriateness to this. A universe whose most obvious feature is darkness, where black space dominates over luminous matter, turns out to be a universe where dark matter and dark energy dominate over ordinary matter and energy. The darkness we see is matched by an even deeper darkness in the universe's composition, components we can't see directly but know must exist. Future observations may reveal more about these dark components. New telescopes, new detectors, new experiments are being planned and built. The James Webb Space Telescope is already revealing galaxies from the early universe in unprecedented detail. Future missions may detect gravitational waves from the Big Bang itself, map dark matter distribution with exquisite precision, or determine the nature of dark energy. Each discovery will deepen our understanding of why the universe is the way it is. But even as we learn more, even as we answer old questions and solve old mysteries, new questions will emerge. That's the nature of scientific inquiry. Each answer opens new avenues of investigation. Each solution reveals new puzzles. The darkness of space, fully explained in terms of current physics, may yet hold surprises we haven't imagined. What we can say with confidence is that the darkness is real, measurable, and understandable. It's not magic or mystery in the sense of being inexplicable. It's the natural result of specific, identifiable physical processes and cosmic conditions. The universe is dark because of how light behaves in a vacuum, because of cosmic history and expansion, because of the structure of space and the distances between objects. This scientific understanding doesn't diminish the aesthetic or emotional impact of a dark sky filled with stars. If anything, it enhances it. Knowing that you're seeing light that has traveled for thousands or millions of years to reach your eyes, knowing that the darkness represents the vacuum of space and the vast distances between stars, knowing that invisible light surrounds you while your eyes detect only the tiniest fraction, all this adds layers of meaning to the simple act of stargazing. The darkness of space is ultimately a gift. It allows us to see individual stars and galaxies, to distinguish one from another, to map cosmic structure. A universe bright with scattered light in all directions would be a universe we couldn't easily study or understand. The darkness provides contrast, reveals structure, allows us to see deep into space and back through time. It's also a reminder of our cosmic context. We live on a small planet orbiting an ordinary star in the outer regions of a typical galaxy. Around us stretches the vast darkness of space, distances so large that they dwarf human scales of reference. This darkness isn't hostile or threatening. It simply is. It's the medium in which stars and galaxies exist, the space through which light travels, the cosmic stage on which the drama of the universe unfolds. Our ability to question why space is dark, to investigate the answer through observation and theory, to arrive at a deep understanding of cosmic structure and history. This ability is remarkable. It speaks to the power of human curiosity and intellect, to our capacity to look at the world around us, ask questions, and find answers. The darkness above us inspired those questions, and pursuing them has led us to profound insights about reality. As you go about your life, remember occasionally to look up on a clear night. Find a dark place if you can, away from city lights, where the stars shine in their full glory against the blackness of space. When you see that darkness, see it not as emptiness, but as fullness, full of history, structure, invisible light, and cosmic meaning. See it as evidence for the Big Bang, for cosmic expansion, for the vast scales of space and time. See the darkness as a window into the nature of the universe itself. Every dark patch between stars is a piece of vacuum, nearly perfect emptiness where photons travel without scattering. Every dark region is separated from luminous sources by distances that light takes years or millennia or eons to cross. The darkness connects to everything we've explored together: the behavior of light, the history of the cosmos, the structure of space, the limitation of human perception. And see the light for what it is too: photons that have traveled across space, potentially for millions or billions of years, carrying information about their source and their journey. Some of those photons were emitted when dinosaurs walked the Earth, or when the first humans were emerging, or before the Sun and Earth even existed. They've been traveling through the darkness all that time, and now they've arrived at this moment, entering your eye, allowing you to see a fragment of the cosmos. The interplay of light and darkness in the cosmos is one of nature's greatest works of art. It's beautiful, sublime, awe-inspiring. The science behind it makes it even more remarkable. Understanding why space is dark doesn't rob it of mystery or wonder. It deepens both, revealing layers of meaning and connection we couldn't see before. So embrace the darkness, appreciate it, learn from it. Let it inspire you to ask questions and seek answers. The darkness of space is not something to fear or ignore, it's something to celebrate and explore. It's a fundamental feature of our universe, as important and meaningful as the light itself. Thank you for joining me on this journey through darkness and light, through space and time, through the questions that have puzzled humanity for centuries and the answers that modern science has provided. The cosmos is vast and strange and beautiful, and understanding even one aspect of it, like why space is black, opens doors to deeper appreciation of the whole. If you enjoyed exploring this cosmic mystery with me, please consider liking this video and subscribing to Nebula Nights for more deep dives into the wonders of the universe. Together, we'll continue to explore the cosmos, one fascinating question at a time, always seeking to understand the beauty and complexity of the reality we inhabit. The universe awaits, filled with darkness and light, with mysteries solved and mysteries yet to be discovered. Keep looking up, keep asking questions, and keep seeking understanding. The answers are out there, written in the light and darkness of space itself, waiting for curious minds to read them. Until next time, may your nights be filled with stars, your questions lead to insights, and your appreciation for the cosmos continue to deepen. This is Nebula Nights, reminding you that even in the darkest sky, there's infinite beauty and meaning waiting to be discovered.